So the important thing to remember about two-dimensional motion is that it's really just one-dimensional motion that you're doing twice. And then when we do three-dimensional motion, that's one-dimensional motion that you're doing 3 times. So we're going to start by going back to vectors. And the way we were using vectors before, using the vector r was for position. And then the vector v was velocity. And recall that velocity was the rate of change of position. So, for example, average velocity we defined as change in position divided by change in time. So now these are all vectors, which means they have components in different directions. Remember we said before that r hat, we defined r hat as having an x and a y component, x times I hat. That's not really r hat, it's the r vector equals x I hat plus y j hat, where x is your x position and y is your y position. Usually x is horizontal and y is vertical, but it all depends on how you're setting things up. And then so your velocity here is change in position divided by change in time, and that's an expression for average velocity. So we're going to do average there. And so you can do all kinds of substitutions on this and come up with the same thing. So for example, we could say since this is change in r here, right? This is change in r. We can say then that this is just the change in x over the change in time times I hat plus the change in y over the change in time times j hat. And basically any sort of reasonable substitution will work here. You can say, if you choose, you can define these as, say, delta x is x minus x naught over t minus t naught I hat. That's the average velocity over the time period from t to t naught plus y minus y naught over t minus t naught times j hat, or whatever you like. I'm saying my j hat got out of the frame there, but there's j hat. So whatever you like. It all follows through naturally and the way you would expect, very intuitively, I think, from our definition of position as this 2 or 3 dimensional vector. The velocity all follows through, and then we had acceleration, which is the rate of acceleration, and that is the rate of change of velocity. And that basically has the same relationship to velocity. The velocity does position. So average acceleration is change in velocity over change in time, which is, we can say, so at this point we need to sort of figure out a way to keep our components of velocity separate. Up here for r, we use this x times I hat and y times j hat. So we had, it in like old form, the way you used to do coordinates and vectors, you might say r is an ordered pair of x and y, that kind of thing. I hope that's not off the screen for you guys. So in order to do something interesting with velocity, we need to be able to express velocity that way. Now, if we could do what we did for position, just pick 2 letters. But the problem is if we keep picking letters, we're going to run out of alphabet before too long because we've got a lot more stuff to do. So the way we do this then usually is to say velocity as a vector is some x component of velocity, which is called v sub x times I hat, plus some y component of velocity, which is called v sub y times j hat. And let's see, that's probably out of the picture, so I'm going to scratch that out and put in a little j hat there so you guys can see that. And then we can also say, we can do the same thing for acceleration. Say acceleration is a sub x times I hat plus a sub y times j hat, and it's all good. So let's look back over here at our expression for average velocity, average acceleration is a change in velocity. So that's going to be the change in velocity in the x direction divided by the time times I hat plus the change in velocity in the y direction divided by time, change in time times j hat. And this all follows very, very naturally and intuitively, and it behaves exactly the way you expect it would. So the net effect of all this is you can break these things down, and you can say in the x direction, and that is meant to be D-I-R-E-C-T-I-O-N. My handwriting is bad, but this pen, frankly, does not pick up all the letters that all the strokes that it should. So I'll try to draw slowly and carefully. We can say in the x direction, we can say our position is x. Our velocity in the x direction is v sub x, and then our acceleration is a sub x. So this is our x direction stuff. And then we can say y direction. Position is y, velocity is v sub y, and acceleration is a sub y. And then, of course, if you want to do z, let's just do z for completeness. It's z, v sub z, and a sub z. So really, this couldn't be any more intuitive. But what's nice is that you can then take any of these and make a one-dimensional equation. So any of these can be done in 1D. So what do I mean by that? Let's if I can, let me see if I can move our stuff down. There we go. Alright, that works pretty well. Oh, that's very nice. Alright, so what we're going to look at now is how we put these things together in 1D. So let's say, where's my pen now? Okay, so here I am. So let's say in the x direction, okay, the x direction, we can say, we can say x equals some initial x plus v sub x 0, which I'm going to say is v. You can do v0 sub x, vx sub 0, it's your choice. Times time. So this is the movement we have due to our initial velocity, and then 1/2 a sub x t squared. Then we can apply that if we have constant a sub x. And then we can use that just like the ordinary equation, the one-dimensional equation, because it behaves just like a one-dimensional motion. The y direction, you can do y equals y naught plus v y0 t plus 1/2 a sub y t squared. So then this becomes for constant a sub x and a sub y. These all work. Wow, this pen is doing a horrible job of picking up. All right, and and then you can apply the velocity equations too. You can say v sub x equals vx naught plus a sub x times t. V sub y equals v sub y naught plus a sub y times t. And these also, require constant acceleration, but that's fine. That's something we can work with. And so, really, what happens is you with these problems, you end up sort of doing what we call decomposing them into an x component and a y component. Let me see if I can find a spot there. That's pretty good. All right. And into an x component and a y component, and just solving each one separately, and then worrying about it later, and then solving each one separately, and generally time, t is the only thing that's really common between them both. So you might solve for like when a certain effect occur, when some condition is met in the x direction, and then say, well, that's and then find the y position where that's going to happen. So let me give you. Actually, we're about done here. So let me just write this in vector form to be super precise. R vector, which is I'll tell you what, let me write R vector equals initial R vector plus initial velocity vector times t plus 1/2 acceleration vector times t squared for constant acceleration. And then this all works out. Wow, this is horrible. Plus, that's a plus sign, and it all works out very nicely because you can say x naught I hat. So x I hat. Nah, you know what? Forget that. You can see how this would then lead you to this equation and this equation. So I'm going to leave it there for now, and I think the next one I'm going to do an example for you.